Welcome back everyone to the course Materials in Sports. In this lecture we will explore the fascinating world of composite materials and uncover why they play a central role in enhancing sports performance. As always, we will look at real examples that show how these advanced materials are changing the way modern sports equipment is designed and used. Let's start introducing the concept of composite. A composite material is a combination of two or more distinct materials that remain separate at a macroscopic level but work together to produce a material with improved mechanical, thermal, or functional properties that are superior to those of the individual components. More specifically, a composite typically consists of a matrix, the continuous phase, and a reinforcement, the dispersed phase. The matrix binds the components together and distributes loads. The reinforcement, often fibers like carbon, glass, or aramid, provides strength and stiffness. Think about this. The quality and size of the interface, that is the region where the matrix and the reinforcement meet, are critical to how a composite performs. If that bond fails, for example through delamination, when the reinforcement pulls away from the matrix, the whole component can collapse. So, what makes a strong bond between matrix and reinforcement? To answer this question, let's look at this graph, which shows the surface to volume ratio for different shapes. The highest surface area per unit volume comes from two extremes: long, thin shapes like fibers, or short, wide shapes like platelets. And that's exactly why the most effective reinforcement materials are fibers, such as carbon or glass fibers, or platelets like graphene or clay nanosheets. Their large surface area means more contact with the matrix, better load transfer, and stronger performance. But surface area alone isn't enough. The matrix and the reinforcement also need to be chemically compatible. That's why reinforcement, like carbon fibers, are often given a special surface treatment. This treatment adds chemical groups to the fiber surface so they can bond strongly with the surrounding resin, usually a thermosetting polymer, most often an epoxy resin. When the bond between matrix and the reinforcement is strong, composites can perform far better than traditional uniform materials. In material science, one of the best ways to compare materials is with an Ashby diagram created by Professor Michael Ashby. These charts let us see trade-offs between different properties and help engineers choose the right material for a given design. On this slide, we have an Ashby plot that compares specific modulus and specific strength across material classes. Both are shown on a weight basis, so strength and stiffness are divided by density. That's especially important in designs where weight matters. Notice how composites sit in the upper right part of the diagram. That position shows their advantage: high stiffness and strength, but a much lower weight than metals. For example, carbon fiber reinforced polymers, or CFRPs, have a density around 1.5–1.6 gram per cubic centimeters. Aluminum is about 2.7 and steel is 7.8 gram per cubic centimeters. In other words, aluminum is roughly 80% heavier than carbon fiber reinforced plastics, and steel is more than 5 times heavier, yet their strength and stiffness are often in the same range. That's why composites dominate in areas like aerospace, motorsport, and high-performance sporting equipment fields, where being light and strong at the same time makes all the difference. The picture becomes even more complex when we consider the layup process. In composite materials, multiple layers of fibers are typically stacked together, and the orientation of the filaments in each layer plays a critical role in determining the final mechanical properties of the component. When all the fibers are aligned in the same direction, commonly referred as the zero direction, the resulting composite exhibits highly anisotropic behavior, meaning its strength and stiffness are maximized in that single direction. On the other end, when the layup includes layers oriented at various angles such as 0, plus minus 45, plus minus 90, the composite approaches a more quasi-isotropic behavior, offering a more balanced distribution of mechanical properties in all directions. The designer's choice of fiber orientation is directly influenced by the type of load the component is expected to bear. For instance, if a part will experience force mainly along one axis, fibers will predominantly be aligned in the zero direction. Conversely, if flexibility or multi-directional performance is required, a mix of orientation will be used. In the resources linked to this lecture, you will find a video interview with Phil White, co-founder of Cervelo, who clearly explains how layup design is tailored to the functional requirements of each bicycle component. For example, the head tube is engineered to be more elastic to absorb impacts from the ground, while the bottom brackets area where the pedals attach must be extremely stiff so that the cyclist energy is efficiently transferred to the wheels rather than being lost through deformation. Besides cycling, which is one of the best examples of composite in sports equipment, many other sports have been transformed by this material. Take sailing, for instance. Sails have evolved from simple pieces of fabric stitched together into advanced laminates reinforced with high-performance fibers like carbon or Kevlar. This technology was pioneered by the US-based company North Sails. Their approach relies on prepregs, short for pre-impregnated fibers. These fibers are carbon, glass, or aramid that are already combined with a partially cured resin. Prepregs are special because they precisely control the fiber-to-resin ratio. This ensures the highest fiber content of any composite manufacturing method. They must be stored cold to prevent the resin from curing, and when it's time to build, the layers are carefully placed according to the design. At North Sails, they developed an ingenious process to mold sails as a single piece, already in their final curved shape. The molds themselves can change curvature depending on the design. In the supporting materials for this lecture, you will find a video tour of their Nevada facility that shows this process in action. The results? Sails are lighter, stronger, and completely airtight. Unlike traditional fabrics, these laminates have no porosity. On top of that, the reinforcing fibers are placed exactly where designers want them, in both orientation and amount, depending on the wind's direction and strength. More fibers where they are needed the most. So, we have come to the end of this lecture. Let's quickly recap the key take-home messages. Composite materials have transformed the world of sport. Their biggest advantage is that they are much lighter than traditional materials. On top of that, their mechanical properties, strength and stiffness mainly, can be fine-tuned through the manufacturing process. This combination of lightness and versatility makes composites a game changer in the design of modern sports equipment. In the next lecture, we will have a deep dive into tennis, where the advent of composites have changed the game entirely.